Good morning, everyone. And today we are going to discuss about finite element analysis on various aspects. Means we are going to solve at least two, three problems. One problem maybe in a 1D, maybe a bar problem will be there, then there will be a spring problem. And also we are looking for an beam elements also. So basically there will be a different elements like a truss element, torsion element, beam element. When I look at the bar element, this is what on a typical bar, which I have being in a displacement u1 here and then u2 here, and we write in a stiffness matrix for this a e by L. This is nothing but in a stiffness of the bar typically, and then 1 minus 1 minus 1 1 like this, and this is a elemental stiffness matrix. So if my bar, if I want to twist it or something, you see, if my shaft is there, this is my shaft. Okay, I'm going to fix it here and I'm going to twist it. So if you look into the bar element, so this is a bar, this is fixed here, and you are applying an axial. Here the variable is theta, and here the variable is in your u. That is what in a field variable becomes in u. Here your theta becomes here field variable. Here force is in bar element, that is a force, and here it is in a torsion element. I can say it is a twisting element is a torque here. And this follows an equation that is force upon area is equal to stress, that is a strain, that is a deflection upon length. So multiplied by stress. This is a typical Floyd follows. That is what it is. How we say this. But in torsion element, we have an equation like an a T by J, G theta by L, okay, and then tau by R. This is what in a relation we already learned it. This is called as a torsion. When we want to convert that entire FE analysis in terms of a torsion here it is a deflection. That's U was in a variable. Here theta is nothing but a variable. So now can I write this equation in this fashion? T by J equal to g theta by L. This is what. And now I have a T as an instead of here it F. And then here, what are, this is nothing but a stiffness of that bar. The bar stiffness, E by L. If I want to determine the stiffness, how can I determine? K is equal to force upon deflection, which becomes an A E by L. And this is what an E. Okay. So we got an a stiffness equation. For torsion equation, how I can get in it? That is what on a stiffness or twisting stiffness. So for that purpose, I can have a T by theta, which is equal to T. Okay, T by theta means it will happen T. I will theta. I will take it to this. Then J divided by L. Now rest is same. So now can I replace this particular part of your equation by T by G J by L, then it becomes in a torsion stiffness. Okay, this is a torsion stiffness, and here it is on a bar stiffness. So then it becomes in a torsion element. So same way we can have on a different elements, but the rest of the matrix remains same. That is what in a 1D analysis we can think of. So we can just look at degrees of freedom for different elements. Here, for this bar element, for each node, we have now only 1 degree of freedom. That is a single degree of freedom. And in torsion also, we have now only 1 degree of freedom. That is, it is a theta for each node. This is the only difference. Okay. So similarly, we'll look at how the elements will be there. If I look at the truss element or bar element, or also it is called as a spar element, all these comes under 1D category, one dimension. Okay. In beam element, so the only difference in the beam element is that what it happens in beam element, if I consider this is my beam, and I'm going to apply the force at the end of this. This is what I'm going to give. And if I divide this into number of element, maybe a three element, I'm going to put it, I'm going to apply the force here, and then it is fixed here like this. So when we are going to separate out a single element out of it, any element you can separate out. If I look at this element, how many degrees of freedom? There will be no 2 degrees. One is one, U1 will be there, and another one, deflection, U2. Another one, this beam is going to rotate like this. Okay. So this is going to rotation of each and every node is going to happen. So that's what I need to provide one more degree of freedom. That is what I can say. It is in a theta 1 for this and theta 2. Means each node I need to have 2 degree of freedom. Okay, for beam element, beam type of element. Reason for this, if you look into the equation of this, I need to take care of the appropriate boundary conditions. If I doesn't consider a twist rotation of this, so if I look at the deflection of this particular bar, okay, deflection of the bar, and if I'm going to apply the force here, and only I'm going to consider the axial deformation, what will happen? Actually, so this axial deformation, this deformation is, so if I consider a beam bar, beam like a structure in this fashion, and I'm going to have one of these beam elements for this. Okay. So if I'm going to apply the force, how it is going to deform? This is my actual original position. It is going to deform in this way. When it is going to deform, it will show me two parts. One is deflection in this direction. Okay, one is this. Another one, there is a rotation about this. The rotation is nothing but a theta. And that rotation will be determined by slope of this. That is what also called as an du by dx. Or I can say if it is 1D, it is I can write in a du by dx. This is nothing but in a sloping boundary condition. That's what each node will have on a 2 degrees of freedom, and that's what this beam element will have on a. If I consider a single beam element, 2 degrees of freedom for this. Okay, one is deformation u, and here it is theta, and then deformation u2, and here it is u1. This theta 1, theta 2 means each node 2 degrees of freedom. One is displacement, another is a rotation, and that's what this this will become on a 4 degree freedom system. That is what it happens. But in bar element, we have seen it is a 2 by 2 matrix. We got it in bar element. But in case of beam element, it becomes on a 4 by 4 matrix. Okay, stiffness matrix will be generated. So derivation of that you can get into some books and you can clear it. It's not on a big deal. In similar fashion, we are going to derive for it. So here we can see it is 1D element, which is spar element or spar or truss element. This truss element is further converted into 2D per node. Having a 2 degrees of freedom. In beam element, we have a 2 degrees of freedom per node for bending in the one single one D analysis. If you look into the plane stress part, it is called as a 2D because it considers an x and y direction deformation. That's what it becomes in 2D. It comes under category of plane stress, plane strain, then axisymmetric. All these comes under 2D of freedom per node. That's what it is a 2D analysis. In this case, if you look into the plate bending or something, along with a rotation displacement, we have to provide a theta also. Then it becomes a 3D. So that is a 3 degree of freedom per. If you look into the thin shale or kind of thing, because in each and every movement means in action, all the three direction it is having a deformation, all the three rotations are there, then it becomes on a 6 by 6. For per node, it has an if I have two nodes, obviously if one node is having a 6 degree of freedom and just taken a two nodes. One is here and another one. It has a 6 degrees of freedom, 6 DOF. Another one is having a 6 DOF. Then your entire elemental matrix becomes a 12 by 12. That is a bigger matrix. So then obviously this can be quite easily handled by computer only. The human cannot handle all this large number of equations. So that is what, and then the last one is 3D, which is solid. That is 3 degree of freedom, and thick shell and thin shell also comes under a 4 degrees of freedom. So if you look into the truss element, this is also called as a bar element. The truss element means I'm going to orient this, I'm going to give a deformation, x direction deformation, y direction deformation, x direction deformation. I'm going to convert whatever this axial deformation in x as well as y. That's what I'm going to convert. Actually, deformation is in only one axial deformation. But because of this orientation, I need to have determine the deformation in x as well as y. That is what it is, a transformation technique we have seen it, and we use. So this is what a typical stiffness matrix for bar element, truss element, or something. So if you look into the torsion element, then from strength of metal, already I told E by J is equal to beta by M. We got so in bar element, this particular element or term, I can say this term is AE by L, and rest is the same. So only the thing is that you need to know this G, J, and L. You need to calculate these all three. Here you need to have an AE by L. So that is what basically a difference between torsion element and okay. Same is with a temperature analysis. Also. See sometime later. If you look into the beam element, already I told there will be 2 degrees of freedom. One is it's a rotation. Another is a deformation. That's what I have on a V is indicates a vertical deformation, and theta indicates my rotational, or I can say it's a slope or strain kind of deformation. Okay? So when we are going to solve this, okay, so we have to have 4 by 4 matrix because it has a 2 degree freedom, 2 DOF here on one node, then 2 DOF on another node. Likewise, I can have a totally, I will get a 4 equations per degree of freedom. I will get a one equation, then that is what I will get, 4 such equation. That's what I will get in a 4 by 4 matrix. So this particular row and this column and row indicates the- this row and this row and this column indicates theta 1. This and the third row and third column indicates then V2, the formation of second node. And this is what like this. And this is what in a matrix, that is what it is derived from basic. So we can have on a same, this is what on a P1 indicates force. Movement also comes into the picture. That is what on a P1 and M1 applied at the node number 1. P2, M2 is applied at the node number 2. Likewise, we got one single, that is a matrix, which is a representation of stiffness matrix. Okay. So we'll solve few examples. This example will solve once again, and this is what in a bar it is stored and applied in a deformations, applied in a forces onto this. So having a 20 mm thickness, then addition to the self weight is also there because of its own weight it is going to deform. That also we are going to take into account. The plate is subjected to point load of 400 Newton, and here it is applied. That is 400 Newton force is applied at this point. And then Young's modulus and unit weight is given. Analyze the plate after modeling it with two elements. Find stresses in element and reactions, etc. So we need to convert that and into FEA model. This is what on a CAD model I can have. This is what an actual model I can have. In FEA procedure, we convert into equivalent representation in mesh and nodes and elements. So I can have this one number node, two number. I can divide into two nodes. two element. One element, I can have on a one element from this point to this point. This is what the representation. Second element will have on this. And what are the two number node? Carries in a force of 400 Newton. And so area for both the cases, both the areas are different, and it is given A1 and A2 here. So obviously, so what is to be done? What is the next procedure? I need to formulate one stiffness matrix for this element, another stiffness matrix for this. This is one thing. I need to formulate a force vector for this element. This is my force vector. Okay. This is another force vector. I can have this is a force vector. This is, I can say it is a stiffness matrix. This is a stiffness matrix and force vector. Then I will have a deflection equation. This is what on a deflection, and this is what on again deflection. Okay? This is one equation and my second equation. So I can now later on I can whichever it is a common. This is a common. It will be get added. This and this part will get added into this, and it will. That is what the procedure will. First of all, determine a stiffness matrix, then stiffness matrix for second element, then this is what nothing but in a common number two will get added it up. Okay. So once we added it up, so here the load is only one point is given, that is a 400, that is a what point load is given. But along with that point load, there is a self weight. That self weight, obviously, as it is an FEA model, what I have to do, total weight may be in a 10 kg. Just imagine it is a total weight is a 10 kg or maybe 100 Newton something. So what is to be done? Half of this should be kept onto one node and half of another one will be kept. Means I can have a W by 2 onto this and W by 2 onto this. So that is what the way we can divide it, because you cannot apply the force in on the within the element. We can apply on the forces on the nodes only. That's what I have to. What I have to do? I have to divide it into two parts and I have to apply onto the individual node. That is what is expected. Then the similar fashion I can have on a weight of this maybe in a W1 something or W2 something. It will be divided half onto W2 by 2 and here on W by W2 by 2 like this. That is what I need to put into the equation. So here how to calculate the weight? Weight is nothing but density into volume, and volume is calculated rho area into length. So that is what area we know, length of element we know, we can calculate volume, and density is already given, that is a zero point 0.8. Then area, volume you can calculate and you can put in. So that will help us to determine 25 plus 25. This total weight of first element is in a 50 Newton. Here it is in a 40 Newton. Okay. And it is divided half onto one node, half onto another node, half onto one node, half. So these are called as in a body forces, because these weights are due to self weight or body forces or maybe attraction forces. That is also it is happening in uniform fashion. It is uniformly distributed. Loads will be divided onto two in case of a two noded element. If it is a three noded element, obviously I need to convert into three different loads. So here, apart from this, what are this body force? We have a point load onto this, that is a 400. So here you can see and node number one, it is a 25, 25. Number two is a 20, 20, and that is what in a point load. I can now go on adding all these forces to result into a one. Okay. And this is what in a total. Okay. Now we can just write this into the force vector. This is force on the node number one, force on the second number node, and third. Like this. I can now substitute into this final equation. This is what a stiffness equation, and then apply the boundary condition. That is what basically procedure to remove which node number one is fixed. So this is what a fixed. Obviously, I need to remove this equation. That is what a Gauss elimination is called. I'll remove this, and this part, this much part will be used for. And it is because this delta 1 is 0 because boundary condition already it is like this. And now I can put up this delta 2 and I can substitute or I can determine delta 2, delta 3 and I can further analysis. So delta 3 we got, delta 2 we got, these two deformations we got, and then I need to determine the stresses. Now, can you tell me in which part there will be the more stresses? So that is what on a physical field we need to get for it. Means what is here I'm going to apply 400. Along with 400 Newton, there is a 50% of load of this part, maybe in a 25. Along with this, the downward part is also 20 is there. That is what in a total load is applied onto this part. And area is 2500. And obviously, this much force upon area on what this part, the stress will be more on this area because if you apply the force onto this, obviously there will be no more less stress on this, like more force. But force we are applied at this point. That's the reason you will get a more stress. And here you can substitute into this. You can determine the forces and then stresses. Stresses is nothing but this is node number one. This is node number two. Deformation of node number one is zero. Two is this much. You can get it. And here you will get more stresses compared to this. Okay. So that is what it is going to happen. And this is having a more stress in this first element than the second element. That is what it matches with our physical understanding. Don't look at all the time numbers. Actually, it should follow certain physical significance, or I can say it is in a physical significance. So that is what we need. And lastly, you can determine the reactions by substituting into this first equation of your stiffness equation and substitute delta 1, delta 2, delta 3, you will get a reaction. And that reaction should be the equal to whatever the forces applied. Just look at the forces, how much you applied it. Node number 1, here we have applied a 400. Okay. Here total weight is here up to this is 50 kg and 25 is applied onto this and 25 is applied. Okay. For this much part, weight is 40 kg, 20 is applied onto this and 20 is applied. So it becomes on a 400 plus 25 plus 20, it becomes on a 4. And this is nothing but an externally applied load, which for 90 somewhere and 90, not 95, 90, and which is exactly equal to your reaction, which is supported by this. This will pull it. So you have an downward direction, it will have a reaction. These two should match. And that is what also one type of convergence. In most of the FEA simulations, it is taken into account. That is force convergence. Similar fashion, there will be another convergence, that is the deformation. In deformation convergence, we know that displacement of the node number 1 is fixed. So obviously that displacement should be equal. You can put back into your equations, try to solve it, determine u1 value. You will get the same value as in a 0 at that location. That is what is called as a displacement curve. And there are a few more convergence criteria. Like there will be an energy convergence, then strain energy convergence, then so many things will be there that we'll look into in detail when we are going to solve a problem in answers. So we'll look at another problem. That is what it is in a similar problem. It is element that is axial load is applied at this node and you're going to solve it. So it is completely converted into denoted element. This is element number 1, 2, and this is 3. 4 nodes are there. Each node is having 1 degree of freedom. Area for each element is given. Even value is different for both the elements. Okay? And you can now solve. So you can get a stiffness K1 here, K2 here, K3 here, all these three stiffnesses. Okay, K1, K2, K3. Then assemble it. This is nothing but a common node where it is going to be added. So these are the two places where it will be seen to be an added. So this is what you got an entire stiffness assembled stiffness matrix, we can say global stiffness matrix. And then look at the forces. Here we are not taken into any kind of body forces. That's what only external forces. And that is on node number 2. That's 200 kilonewton. That here displacements are given. And for this, we have fixed bone nodes. That is what here it is. And this is also fixed. That is U1 is fixed and U4 is fixed. Only I need to determine these two different. So I can now put into this equation. Obviously, this node is fixed. But I will remove this U1 equation from my entire global stiffness matrix. And also I will remove fourth equation. That is what a U4 equation for global stiffness matrix. And this much part is left for your solution. Okay. And this we can put into equation. You can get an U4, U2, U3, and all these equations, and you can solve it quite easily. Okay. Then second equation you will get an U2, then U1, U2, and U3. You can solve U3 somewhere we got these two numbers. Then you can put up the reactions R1 and R2. And if you look into this reaction, this is what 151 and 48 reactions. So what these reactions indicates, if I add these two reactions, it will result into 200 Newton, 200 kilonewton, which is nothing but an external force applied on the node number 2. So that is what the way you can verify. That is what cross check you can do it. Another one you can determine the stresses also. For node number 1, you can get a stress value 63. Another one, element number 2, we get a stresses minus 81 something. It is compression because you can just look at the construction of your entire elemental uh, equations. Force is applied at this one. Obviously, this will be in tension. This too will be in a compression because it is fixed with this two. And obviously, this will come into the compression. This will be the tension. Tension will have a positive sign. Here it is a negative sign. This also will have a negative sign. That is what the physical understanding or physical significance can correlate. So there is a method as elimination we have seen, and we can think of to go for penalty approach. So we'll look at penalty approach problem. Okay, in penalty approach. Okay, okay. Here it is a penalty. So then we will look at another problem, that is estimate the displacement vector and stresses reactions for stress structure. So in stress structure, you can just look at the force is not exactly applied at one direction, but it is applied at a particular angle. So obviously, this 500 Newton can be resolved into two components. One is vertical, another is a horizontal. That is what I need to do. So this can be converted into 500 sine theta, and then 500 cos theta. And we can get these forces, yeah, vertical force and then horizontal force, and you can apply it particular. So for this purpose, we can have a stiffness matrix K is equal to A by L and something, and these are the nothing but in degrees of freedom. This is node number 1 in X direction, node number 1 in Y direction, 2 in X direction, node number 2 in Y direction. So we have a length for each nodes and each element, that is L1, L2, L3. And then only we need to determine these L's. These are L are nothing but in a direction. Also called as in a DCS. So we need to determine these DCS. DCS is quite easily determined by L here and M. We can have an X2. When you are looking for an X1 and X2, it becomes an L, and then if you are looking for Y variable, then it becomes yeah. There is you can directly, if you know the theta angle, you can determine L is equal to cos theta. This is one, and M is equal to sin theta. That is also the way by which we can determine. So we can get an L here. So similarly, I will get a stiffness matrix for element number 1. Then element number 2, I will get a stiffness matrix. Element number 3, I will get a stiffness. So I'll get all the 3 stiffness matrix. I need to create an assembly of it. Okay. Then assembled stiffness matrix will be seen it here. So after assembly, you can just see there will be a much more addition kind of things. And then we need to apply the boundary conditions where the displacement we need to look at U1, V1, V2. These 3 degrees of freedom are these are applied a boundary condition and these are fixed. So now the load displacement relation reduces to this. Now we'll get in a 3 by 3 matrix and then we can go on determining what are the rest of the degrees of freedom, that is U2, V2. So we can substitute into this, you will get in a stresses. We can get in a stress in element number 1, stress in element number 2. But basically you can go. So here we can determine the reactions. You can get in a reaction at first equation, you will get here. Then third equation, you will get reaction. And third, fourth, that is maybe in a fourth equation, somewhere you will get in this reaction. That is what the way you can solve this. If you look into the equilibrium of this entire stress, because equilibrium here it is a 100 Newton and 250 Newton. And if I cos theta and sin theta, if I match it, it becomes a 500 Newton force at angle theta is equal to 30 degree to the horizontal. So if you resolve it and come back to that particular reaction force, you will get it. And this is nothing but a cross check where you will get a perfect answer. So this is what the way you can solve truss problems, beam problems, and kind of. We'll now look at one problem on the beam because beam problems are more problems on the beam. So here it is in a beam. So up till now, whatever the force was applied horizontally, this direction or this direction. But now forces were applied vertically, and that's what it becomes in a beam. In this beam problem, this whatever the relation that is a stiffness matrix, you already know it because we have seen in previous slides. In this, concentrated load of 50 kilonewton is applied at the center of the beam, and that entire length of the beam is 303 meter, and depth is 200 mm, width is 120 mm. Calculate deflection and slope of midpoint. Okay, so this depth and width will be used to calculate this I. Length is already that is by 1500, and E value is already given. And then finite element model will be one element here, and then second element. Node number 1 will be here, node number 2 will be here, and node number. And each node will have a 2 degrees. One is vertical deformation, E I can say, and another is a theta. Even theta 1. Likewise, I can have each node will have a 2 degrees, and each element will have total 4 degrees. That's what I will get in a stiffness matrix. This. So here I can have a V1, theta 1, V2, theta 2. So we can put these values. So this is what an I is calculated by simple formula BT cubed by 12, and this was 120. This will be taken into account depth and this BD cube or BT cube. And so once we got this, then we can have an assembly of this. Assembly is quite easy because this nodes, for this node, there will be 2 degrees of freedom. One is V2 and another is theta. Means I need to have, this is what on a V2 equation, this is my theta. Okay. So here also it is a V2 equation and this is my theta. I need to add up these two equations and ultimately we'll get an only 6 by 6 matrix. Okay. So that we'll see it here. You can just look at this equation is added here. 1, 2, 3. This is also added 4, and that is what this also get added into. This is what the way it is added into your, and you will get a deformation, or that is a entire global stiffness matrix. This global stiffness matrix, okay, indicate here it is in a force, movement, force, movement, and here it is a W1 theta 1, W2 theta 2, W3 theta 3, because these two are nothing but in a common. Obviously, addition of these elements will happen from these two. So then you can apply the boundary conditions. For first node and last node, this node V1 and theta 1 is 0. So both are 0. Here V3 theta 3 are 0. Means I have to remove this V1 equation here, theta 1 equation here. Obviously, I will remove the vertical lines also. That is the column also. This is one column. This I remove. And W3, this is my W3. This is theta 3. I will remove it. So likewise, I can get an only this much part will be used for analysis. That is a 2 by 2 matrix. So you can now take this into this, then V2 theta 2, and then put V2 M2 here. Apply the forces. If you apply the moment also, moment you are not applied onto this. That's what I'm going to put this moment equal to 0. Here it is minus 500 Newton. And then I can now get this V2 value here that comes to 1.3. And this theta 2 is showing an a 0. Why it is showing 0? Because the length of the both the beams are same. This is L as L, and this is having the same. And when I'm going to apply the force onto this will deform in this fashion. And there will not happen any kind of a deformation of the rotation of the node. Deformation will happen. That deformation is 0.34, 0.4395. But there will not be any kind of rotation of this node. That's what this theta 2 you're getting. And from strength of material, you will get the same number here. And that is the same kind of number. That's what we can be assure that the beam analysis were done as perfect. So this is what the way you can do on a beam problem solution. And another beam problem will look at the same here. That is a 500 meter and 5 meter and 500 meter. That is the total length of the beam is 10 meter, and one force is applied at 20 kilonewton. You can add up some movement also here in later stage for understanding purpose. Here there is no movement as such. Then inertia is given, moment of inertia is already given. You need not to calculate separately, and you can determine deflection of the deflection under the load, and shear force and bending moment, and reaction angle. So here in this case, we need to have a displacement vector here, then stiffness matrix. Already we see this matrix. So I can now have two elements. I have to have two stiffness matrices. So K1 is here, then K2 is here. This is EI by L something. What it is calculated here, LQ. Same it is calculated for this particular element. Then assemble it. When you are assembling this 3, 4, these two equations and these two equations, uh, that's what they will get add up, and it will be added in this particular locations, and plus minus it will convert into and numbers. So this is what the way you can do determine the global stiffness matrix. Once we got this global stiffness matrix, obviously we need to apply the boundary conditions. This boundary conditions delta 1, delta 2, delta 5 are 0. Then rest is only 3 degrees of freedom are left for us, because here boundary condition is that here this boundary condition, this deformation is allowed. Okay? Means deformation is allowed. Only the rotation is also allowed. That is what it does. That's what 3 by 3 matrix. And then you can substitute all this and we'll get a deformations for delta 3 and delta 4. Okay, and delta 6 is nothing but a rotation. You can now put this into equation. You can determine the reactions, end movements, and all these things. And you can determine shear forces and all things. Here it is a moment is calculated, then moment is calculated when a 31.25 Newton, and shear force is also 31.75 Newton, and that is what the way you can calculate. Then end reaction.